Welcome to 6.2 Newton's Law of Gravitation, day 2 of 2. So this is the slide that we finished off with last time. We went through this multiple choice question, we went through the answer. If you want to review the solution to this, check out the end of 6.2, day 1 of 2. Okay. So moving on, we're going to start moving on to the topic of Keplers laws. So Kepler essentially was trying to come up with some kind of expression to model the orbital radius of the planets in our solar system to the orbital period. So essentially the distance they are from the sun to how long it takes them to go around the sun once. And he actually found the relationship t squared is equal to 4 pi squared over gm all times r cubed. Okay, what I want to point out here, and we'll come back to this idea again, is that this value in the brackets, the 4 pi squared over gm, that's a constant. The 4 pi squared and the g, those are definitely constants by definition. M, that is the mass of the central body about which the other object rotates at or orbits at radius r with the period t. So that has to be constant. What differs is the distance of the planets from the sun r and how long it takes them to orbit t. Okay, so we see a bit of a proportionality here. Again, we'll come back to that idea. So we have to derive this expression. Okay, so let's go to the paper mode here and derive it. Okay, so what we want to start off with is, well, we know that the fact that this object is orbiting is due to the gravitational force. And the gravitational force here is the centripetal force. So Fc is equal to Fg. Now, Fc, that's the centripetal force. We know the formula for that is mv squared over r. Okay, g, or Fg is rather gmm over r squared. Okay, so now you see you have an m on both sides. The mass that you're going to cancel, that's the mass of the orbiting object. The capital M that remains, that's the mass of the central host. So let's say the sun. Or if it's the moon orbiting around the Earth, that would be the Earth. I've got one r on both sides that I can cancel, so that's gone. So I'm left with v squared is equal to gm over r. Okay, so how's that getting me closer to my answer? Well, speed. When you have an object in orbital motion, okay, so we talked about this in the last video as well, the distance that the object travels in the circular path is called the circumference of the circle. Right, so that's 2 pi r. And the time it takes for it to go around one complete time is called the period. So the time is just capital T. So what I'm trying to do here is make a substitution for v, since v does not appear in the expression that we're trying to derive. Now I know that when you have no linear acceleration, speed is equal to distance over time. Okay, so distance is 2 pi r, and time is capital T. Now in my expression I have v squared, not v. So I'm going to go ahead and square this. It's going to be 4 pi squared r squared over t squared. So I take that and I plug it in over here. So 4 pi squared r squared over t squared is equal to gm over r. All right, so what I'm going to do is I'm going to take this r in the denominator and I'm going to multiply it to the top left. And I'm also going to take that t squared and multiply it to the top right. So 4 pi squared, this will be r cubed, is equal to gmt squared. You know, I'm trying to get the expression for t squared, so I'm going to divide left and right side by gm, and I'm going to be left with t squared is equal to 4 pi squared r cubed over gm. Okay, I mean, that's essentially what we're trying to derive. It's written a little bit differently in the slides, and the reason for that is they're just isolating for the constant. So 4 pi squared over gm, those are the constants, and so we can actually write this a little bit differently. So t squared is equal to the constant, so 4 pi squared over gm times r cubed. Now you might wonder, okay, what's the difference between writing it like this and like this? Well, like this, it's easier to see that there's some kind of proportionality between t squared and r cubed. And in fact, let's go back to the slides here. That's essentially what Kepler determined. He didn't actually determine the constant of proportionality. He determined that the square of the orbital period is proportional to the orbital radius cubed. Okay, so the solutions on the slides are exactly what I just did. All right, so let's move on. Example, a satellite in geosynchronous orbit takes 24 hours to orbit the Earth. I want to just pause for a second there. The word geosynchronous. Geosynchronous means that the satellite will have the same orbital period as the Earth has rotation period. Okay, so it takes 24 hours for the Earth to rotate once on its axis, hence the length of a day. Okay, so for a satellite that takes 24 hours to orbit around the Earth, we call that a geosynchronous satellite. Now, what's really interesting and kind of curious, maybe coincidental, maybe not, is that the moon, the Earth's moon, is actually a geosynchronous satellite. Now, our moon is a natural satellite, of course, but it takes, it takes about 24 hours to go around the Earth once, hence why the moon will generally appear in the same spot on the sky every single night. Okay, so that's interesting. Now, it can be a man-made satellite that is also taking 24 hours to orbit around the Earth. Okay, thus, it can be seen above the same point of the Earth's surface at all times if desired. Find the necessary orbital radius and express it in terms of the Earth's radii. Okay, so to find the orbital radius, let's go back to webcam mode here. All right, so moving on. So now we're in our next example. So we know that this satellite is in geosynchronous orbit. So we've got the Earth, we've got some kind of a satellite that's orbiting around the Earth. Okay, now it's taking 24 hours to orbit around the Earth once. Now, if I do have to use that value in my calculations, I can't plug in 24 hours. In physics formulas, whether it's this one or any one, you always have to plug in SI units. And the SI unit for time is seconds. Okay, we have to find the orbital radius. So in fact, it'll make sense that we most likely will eventually have to come up with this value in seconds. Okay, so in order to find the necessary orbital radius, let's just use this formula right here. So t squared is equal to 4 pi squared over gm times r cubed. We're looking for r, so we're going to rearrange this. So it's going to be gm over 4 pi squared. Okay, and then we're going to have t squared, and then that's equal to r cubed. So those got multiplied, these got divided. Yeah, that looks right. Okay, so g is a constant, 6.67 times 10 to the minus 11. M, okay, so this is a geosynchronous satellite. This is regarding the Earth. So this capital M is the mass of the Earth. Back in actually the same lesson, 6.2, but day 1 of 2, we saw that the mass of the Earth was 5.98 times 10 to the 24. We're going to divide that by 4 pi squared. Okay, now we have to multiply by t squared. So again, make sure your t is in seconds. So we're going to do some conversion here. So 24 hours, if we convert that to seconds, we have to multiply by 1. We keep our 1 as a blank empty fraction. So 1 hour, hour goes on the bottom since we're trying to cancel it out. 1 hour is 60 minutes. Okay, so let's put 60 minutes on top. And then we're going to convert that minutes to seconds. 1 minute is 60 seconds. Okay, so this way my minutes cancel and my hours cancel, and I'm left with seconds. So 24 times 60 times 60. So grab your calculator. 24 times 60 times 60. So 86,400 seconds. The more you do problems like this number will start to look familiar to you. So at least you'll become comfortable with using that kind of a value. So t is 86,400. That's what's getting squared here. So 86,400 squared, and that's equal to r cubed. Okay, so let's punch all this in. 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24. Let's just do times 86,400 squared equals divided by 4 pi squared. Okay, so this value that you see here on my calculator screen, that's r cubed. Okay, so I'm going to take the cube root. Okay, so we're getting r is equal to 4.2, let's call that 4.2 times 10 to the 367. 4.2 times 10 to the 7 meters. That's a pretty big number to try to gauge in your mind, okay? And that's why the question says, give it in terms of Earth's radii. Okay, so Earth's radii is given in the question. So yeah, technically the Earth's mass should have also been given, but nonetheless, there it is. So to figure this out in terms of Earth's radius, well, again, you're changing units. So you multiply by 1, and that 1 is a blank empty fraction. So I know that 6.37 times 10 to the 6 meters is 1 radius of Earth. Okay, this way my meters cancel, and I'm left with this value here divided by 6.37 times 10 to the 6. Okay, so the units I'm going to be left with are RE. So that's about 6.6 radiuses of Earth. Okay, so that's a little bit more easier to manage, I guess, in our heads. Easier to understand. Okay? All right, so going back to the slides. So this is the same solution that you see. Okay, next. Which of the following expressions correctly relates the radius r of the circular orbit of a planet around a star to the period t of the orbit? So in order to answer this, you really just have to remember Kepler's law. And we saw the formula before, so I'm just going to quickly switch back to the paper screen here. Okay, so remember, we came up with this formula right here, and this is what we were actually asked to derive. T squared is equal to some constant times r cubed. Okay, so whenever you have two things that are equal to each other times a constant, that means they're proportional, right? So for example, let me just pop down here for a second. I'll just use this space. Remember, if A is proportional to B, A and B are some kind of variables. If these two things are proportional, then A is equal to a constant times B. You can even write B is equal to a constant times A. That constant will just be different, okay, where K and C are elements of the real numbers. Okay, so that's the case. Now here, this is just a constant. So you can just call that K if you want. So in other words, T squared is equal to K times R cubed. And therefore, T squared is proportional to R cubed. Okay, so that's pretty much what we've got here. So going back to the slides, okay, T squared is proportional to R cubed. None of the other ones, T squared is proportional to R cubed. None of the other ones correctly match. So the answer therefore has to be A. Okay, and the explanation is here, although we just talked about it. And so this little piece at the bottom of the slide is just going back to that idea that I explained, that Kepler, he didn't actually know what that constant of proportionality was. He knew that they were proportional, which was a big enough discovery on its own. But it wasn't until Newton and his universal law of gravitation that, well, it was determined finally what that exact constant of proportionality was. Okay. Let's see, next. The rings of Saturn are made of rocky particles that orbit the planet. The period t of each particle depends on its distance r from the center of Saturn. The period t is proportional to r to the n. Which one of the following is n equal to? Okay, so period t is proportional to r to the n. So before we just kind of jump the gun here, we have to remember Kepler's law. So going back to our page here. Okay, so from our earlier look, we've got this formula, t squared is equal to 4 pi squared over gm times r cubed. Again, it's just a constant. So I know that t squared is equal to some constant times r cubed. Oops, there we go. T squared is equal to some constant times r cubed. So t squared is proportional to r cubed. We want to know, well, that t is proportional to r to the n. So that means I need t to the power 1. Right now, t is to the power 2. And so really all that means is I have to, well, figure out how to isolate t. Okay, so some of you might look at that and say, well, I need to take the square root. And that's fine. That is technically what we're doing. Another way to look at it is I'm raising both sides to the exponent 1 over 2. So the left is to the 1 over 2, the right is to the power 1 over 2. Okay, so that for exponent to an exponent rules say I multiply. 2 times a half is 1. T to the 1 is effectively t. And on the right side, I have t to the 3 over 2. Well, 3 over 2 is 1.5. So that tells me that n is equal to 1.5. And the answers given in the selections are all decimals. So going back, here we go. The only answer here that actually makes sense is B, 1.5. Okay, it's for exactly the same reason that we just explored on the sheet. Okay, moving on. Two satellites, X and Y, move in circular orbits about the Earth. The orbital period of satellite X is 8 times that of satellite Y. So the ratio of the orbital radius of satellite X to the orbital radius of satellite Y is. Okay, so you would have seen problems like this many times throughout your homework or the practice or even the tests. You're given the value of one variable relative to another as a factor or a ratio, and you have to find the ratio of some other kinds of variables. Okay, so let's go to the paper screen here. All right, so we are told in the question that the orbital period of X, so everything that I'm told, I want to write down and translate into mathematical language. The orbital period of X is 8 times the orbital period of satellite Y. Tx is equal to 8 Ty. All right, now we are asked to find the orbital radius of satellite X to the orbital radius of satellite Y. Okay, so this is what we have, this is what we're looking for, and well, the expression that we know to be true is that t squared is proportional to r cubed. Okay, Keplers Law. So t squared is proportional to r cubed, then t squared is equal to a constant times r cubed, or you can see it as a constant times t squared is equal to r cubed. It doesn't matter which side you put the constant, just keep in mind that they would technically be different constants. Okay, I'm looking for rx over ry, so we're using capitals here, so I'm going to just change this to a capital. All right, so we're replacing r. So r cubed is equal to some constant times t squared. So now to get r by itself, we're going to raise both sides to the power of 1 over 3. Actually, let me try to do this with a pen. I hope it shows up on the webcam. Let's give it a try. That's not too bad. Okay, we're going to raise both sides to the power 1 over 3. Right, what you do to the left, you have to do to the right. This way we're isolating for r. So 3 to the 1/3, that's 3 times 1/3, which is 1. So you get r as we expect. Here we're going to have c to the 1 over 3 times t to the 2 over 3. Now I just want to point something out here. A constant cube rooted is still a constant. That's really what you care. It's just going to be some value. So you can replace that with a new letter if you want. You can call it w, or you can leave it as c to the 1/3. It's up to you. Okay, but this is what we're going to be using, and we're going to be plugging these expressions in here. Okay, so we're looking for rx over ry. Okay, now I know r is equal to some constant to the 1/3, which will be the same for both, times the period to the power 2/3. So if it's rx, it'll be tx to the power 2 over 3, and over c to the 1 over 3 times ty to the 2 over 3. Okay, so what I can see right away is that my constants are canceling, and so they are irrelevant. Okay, so those are gone. And now I have tx over ty. All of my possible multiple choice options are just integers. So I have to get rid of these variables somehow, and I do that using that expression right there. Tx is 8ty, so I'm going to replace it here. All right, so I've got tx to the 2/3 over ty to the 2/3, and tx is 8ty. Okay, so if I have two things or more things getting multiplied and or divided in a bracket, and I have that everything raised to an exponent, that exponent gets applied to everything inside of the brackets. Okay, so that means it's, let me move this up. I've got 8 to the 2/3 times ty to the 2/3 over ty to the 2/3. Okay, so guess what? Ty to the 2/3, those cancel. They are the same. So I have to figure out what 8 to the 2/3 is. Now, before you go and reach for your calculator, try to figure this out on your own, because you can do this. Okay, and it shows that you actually understand how to rearrange this expression into a radical. Okay, so 8 to the 2/3 is the same thing as the cube root of 8 squared. So what number multiplied by itself 3 times gives you 8? That's 2. If you square 2, you get 4. Okay, so that tells me that the radius of x over the radius of y is equal to 4. So that is that's my final answer here. Okay, so going back to the slides, the answer has to be B. So I'll just put up, again, the typed up solution, and hopefully the written solution was a little bit easier to follow. Okay. All right, so here we go. There's Dobson again. Okay, so Dobson showed up in an earlier part. Dobson's now inside of an elevator, which is not moving. All right, so instead of having ice cream this time, he has a ball in his hand. Okay, so he's in an elevator. The elevator is not moving, so therefore it's not accelerating. If he drops a ball, it will accelerate downward at 10 meters per second squared, as expected. Okay, so that 10 is just the 9.8 rounded. Okay, this is what we would expect, the acceleration due to gravity. Okay. If the elevator is accelerating upward at 2 meters per second squared, what will Dobson observe the drop ball's acceleration to be? All right, so really we have a couple of options here. Either the ball's still going to accelerate at 10 meters per second squared, it's going to accelerate faster due to the 10 plus 2, or it's going to accelerate slower at 10 minus 2. So if you actually just visualize the situation, it's not that difficult to determine. Okay, so originally, so I've got this ball in the elevator that's not moving, and it just accelerates down at 10 meters per second squared. Again, if this is the ceiling and the floor of the elevator, they're not in motion. Now you have this ball that's accelerating down at 10 meters per second squared, then now the actual elevator is accelerating up. That means the ceiling accelerates up and the floor accelerates up together, right, at 2 meters per second squared. Now, if you can visualize that, if this piece is coming down the ball and the floor is going towards the ball, that means they're going to reach each other much faster, right? So they're going to close the gap in less time, giving the, I guess, almost like the observation or like an illusion of this ball accelerating faster, right? So if it takes a certain amount of time when the elevator is stationary to hit the ground, okay, if in a different scenario it hits the ground faster, well, you would think in your head that means it's accelerating faster. But what you don't realize is that the frame of reference that you're in is actually moving up. Okay, so in this case, you have the acceleration at something higher than 10. So 10 plus 2, which is 12 meters per second squared. Okay, so that's what Dobson observes it initially. Okay, so that's what's written on the slides. Okay, now the last piece there, although it was not part of the question, the last bullet point there just addresses the opposite scenario. If the elevator was accelerating downward at 2 meters per second squared, okay, well now it would take the ball even longer to catch up with the floor of the elevator. So it would look as if it was accelerating much slower, at 2 meters per second squared slower, which means he's at 8. Okay, next. Practice. If the elevator were to accelerate downward at 10 meters per second squared, what would Dobson observe the dropped ball's acceleration to be? Okay, so again, going back to this. The ball we know is accelerating down at 10 meters per second squared. If now the floor is also accelerating down at 10 meters per second squared, how is the ball ever going to reach the floor? They're both going to increase in speed at the same interval in time. Every second, their speed will keep increasing. So the ball should never catch up with the floor. In other words, the ball, if it never catches up with the floor, it's going to look like it's just hanging around in the middle. So they're both falling together. Okay, so this is actually making us think about what's happening in Hollywood movies. Okay, so in Hollywood movies, when a cable of an elevator gets cut and the elevator starts to fall, the people in the elevator usually get pushed up against the top of the ceiling of the elevator as the elevator is crashing down towards the main floor. Now, one of the questions I'm going to have you thinking about this week is, well, is that real? And if so, can you explain it using physics? If it is not real, explain it using physics. Okay. All right, back here. Now, there's a bit of terminology on this slide. Okay. He would observe the ball to be weightless. Okay, so we have to be very careful here because that term weightless is often used incorrectly by the media. Okay, so weightless by definition of physics means your body is only in free fall and you have this absence in the sensation of weight. So you don't feel as though you have weight. Okay? The only reason you feel as though you have weight is when there's some normal force pushing up against you or some other kind of force pushing against you. If you are in free fall, in other words, the only force acting on you is the force of gravity, how are you to feel your weight? Okay, so that's what weightlessness means. I just want to actually write this down so you formally have it in your notes. Okay, so weightlessness, when your body is in free fall. Okay, so that means that only Fg acts on you. Only force of gravity. There's no air resistance, there's no normal force, nothing like that. So this is the absence in this sensation of gravity. So even though gravity is the only force acting upon you, you don't actually feel that gravity since there's no force to oppose it. Okay, so going back to the slides here. All right. There is a type of plane called the vomit comet. Okay, so it essentially tries to give the illusion to people who will pay a certain price of what weightlessness would feel like, almost as if they were in space, although this all happens on Earth. So if you're more interested in learning about this, feel free to take a look at this in more detail. But we're going to go ahead and skip to the next slide. Okay, our practice. We have all seen astronauts experiencing weightlessness. Explain why it only appears that they are weightless. Okay, so it appears as though astronauts are weightless. So for example, we've got a picture of an astronaut here just balancing some tomatoes. Well, the tomatoes are not going to accelerate down. The astronaut is not accelerating down any faster than the tomatoes or vice versa because the only force acting on them is gravity. Okay, so that's the only acceleration acting on both of them. And if they all have the same acceleration, well, one is not going to move faster than the other. So it will appear as if they're all in static position relative to each other. Okay. All right, discuss the concept of weightlessness in deep space. Okay, so this is actually a really nice photograph. This is a photograph of something called the Hubble Deep Field. Okay, so essentially, some very powerful telescopes were pointed in various points of the sky for extremely long periods of time to gather this image of all these galaxies. So to give you an idea, if you were to pick one of these galaxies, and let's not be too generous here, let's pick this one right here, let's say. If this looks kind of like a spiral galaxy, okay, even these ones here, these are spiral galaxies. Imagine each of these galaxies has billions of stars, and our star is just one star upon which our solar system exists. Our solar system is big enough, let alone when you start thinking about, well, the galaxy, and then you have clusters of galaxies, and then clusters of those clusters of galaxies. I mean, it's just mind-blowing. But the idea is this: between all of these galaxies, I mean, it's pitch black. There's no stuff. Okay? At some point, you might even find a region of space that is close to a vacuum, almost no particles. Okay, so if you don't have any object close to you, relatively speaking, how are you to feel the sensation of gravity? How are you to feel attractiveness towards them? Okay, so that's the idea. When you're far, far away, when your R value is very large in the universal formula for gravitation, your force becomes almost zero. Now, it will never actually be zero, but for our intents and purposes, it's essentially zero when you're far enough away from these objects of mass. All right, let's keep going. A satellite of mass m and speed v orbits the Earth at a distance r from the center of the Earth. The gravitational field strength due to the Earth at the satellite is equal to... Okay, so this calls for some more solving on paper and pen. All right, so let's switch modes here. Actually, let's just go through that problem one more time. Let's see, we have a satellite of mass m and speed v orbiting the Earth at distance r from the center of the Earth. We want to know the gravitational field strength. So what we're looking for is lowercase g. Remember that when variables and letters are given to you in a question, you can only have those letters in the answer. So I'm only given the letters m, v, and r. So at most, I can only have up to those 3 letters in my answer. Okay, so let's go here. All right, so the way you want to think about this is, well, what is causing the satellite to orbit around the Earth? Okay, the satellite's orbiting around the Earth due to force of gravity, and that force of gravity is a centripetal force. So this starting piece should look very familiar to you. So Fc is equal to Fg. Now the centripetal force is always mv squared over r, and Fg is gmm over r squared. Okay, so r is the distance from the satellite, v is the speed that it orbits, lowercase m is the mass of the satellite. The satellite mass is the one that goes here, and that's the one that gets canceled out from both formulas. Okay, so we have mass canceling out, we have 1r canceling from both sides, so we're left with v squared is equal to gm over r. Okay, now remember we're looking for gravitational field strength. We're looking for g, okay, lowercase g. G is not coming out of this expression, but there was another equality that we looked at where G did come out of, and that was setting the 2 expressions for force of gravity equal to each other. F little g is equal to F capital G. So mg is equal to gmm over r squared. So once again, the masses cancel. Now here's your expression for lowercase g, gm over r squared. Now, g is a constant, so you could technically have that in your answer. That's just a constant of nature. That's fine. R is there, but the problem is we have m. This is the mass of the Earth, and that capital M was not given to us, nor can we plug it in. So we have to figure out an expression for capital M. That's where this equality comes into play. Okay, so I can rearrange this for m. So m is going to be v squared times r divided by g. So I'm going to take that and plug it in over here. So g is equal to g over r squared times m being v squared times r over capital G. So my g's will cancel, and you have 1r canceling from top and bottom, leaving you with v squared over r. So that is the value for the acceleration due to gravity. My advice: don't memorize any of these types of formulas, okay, because every time the situation is going to be a little bit different. What you need to remember is you can always set centripetal force equal to gravitational force. That usually is going to help you get to the answer somehow, or at least help you simplify like it did in this case. And you can always set the 2 forces of gravity equal to each other to help you solve for acceleration due to gravity. Okay, so just remember these strategies. Okay. So that looks like the answer is v squared over r. Going back to our slides, v squared over r appears in part B. Okay, so here we go. So the typed up solution is here, but the answer is in fact B, like we found. Okay, a satellite of mass m orbits a planet of mass capital M and radius capital R, as shown. So the diagram is not to scale. The radius of the circular orbit of the satellite is x. The planet may be assumed to behave as a point mass with its mass concentrated at the center. Part A, deduce that the linear speed v of the satellite in its orbit is given by the expression v equals root gm over x. Okay. All right, this is actually going to be pretty simple. So let's go back to our paper here. We're pretty much there already. If you had to answer this question from scratch on a test, you would of course start with this equality. Fc is equal to Fg do your equalities and work your way through. Now, since we already did it, just for the sake of time, I'm going to start from this expression right here. Okay, so I know that v squared is equal to gm over r. Okay, now in this case, r is the radius of the orbital motion. In the slides, capital R is the radius of the planet, and x is the radius of the orbital motion. So I'm going to change that r to an x. So gm over x is equal to v squared. Well, it just takes a really simple rearranging to solve for v. Square root. V is square root of gm over x. And that is part A done. So this is example part A. Okay. Hopefully not too bad. So going back to the slides now. Of course, there's the typed up solution. Okay, B, derive an expression in terms of little m, capital G, capital M, and x for the kinetic energy of the satellite. Okay, again, you can only use those letters. So going back to the paper here. So kinetic energy. Well, there's only one formula that you've learned for kinetic energy. Kinetic energy is 1/2 mv squared. Okay, so v is equal to the square root of an expression. So if I just want to square that, I effectively remove the square root. So v squared is gm over x. Okay, so I'm going to plug that in over here. The mass, it's the kinetic energy of a specific mass. Let's see. The kinetic energy of the satellite. Be careful here. Okay, so the satellite has mass little m, so I don't want to change that to a capital M. Okay, but this speed, this is orbital speed of an object at distance x from a mass capital M. Right, this is the host mass. This is the satellite. So you don't change the masses. There should be no cancellation or increasing of exponents if you multiply them. No, they have to be different m's. So effectively we have here m over 2 times v squared, and v squared is g capital M over x. Okay, and that's essentially it. You can merge it into one big fraction, but that's the answer there. So going back to these slides. All right, the next topic here is a binary star. Binary, well, the prefix bi means 2. Okay, so it's a 2-star system. Now, usually these 2 stars orbit each other. What's really fascinating about our sun is that until about very recently, the sun was always believed to be a solitary star because it didn't appear to be orbiting around a different star. And there are many theories coming out to suggest that there is actually another star that orbits the sun and the sun orbits it about some central place. But anyways, we won't get into that too much. Here we have a set of binary stars orbiting about a fixed point P as shown. All right, so the stars have the same orbital period capital T. Each star may be considered to act as a point mass with its mass concentrated at its center. Okay, all that means is that we can use Newton's law of universal gravitation. The stars of masses m1 and m2 orbit at distances r1 and r2 respectively from point P. Okay, so there's point P in the middle. Part A, state the name of the force that provides the centripetal force for the motion of the stars. Okay, so, this should be pretty clear. It's the gravitational force. Okay, so nothing mysterious about that answer. Part B, by considering the force acting on one of the stars, deduce that the orbital period capital T is given by the expression, and there it is. Okay. So we've got an interesting looking expression there. Now, part of it should look familiar to you. Maybe not the R1 plus R2, but part of it should look familiar, and that looks kind of like Keplers Law. And think about then, how did we derive Keplers Law? Well, we did that using equating centripetal force with a gravitational force. Okay, so let's jump back to the paper here. Okay. Now, I'm just going to quickly write here the formula that we're trying to derive overall. We're trying to get to t squared is equal to 4 pi squared over gm2 times r1 plus r2 all squared. Okay. Now, mass m2 is at orbital distance r2, Mass m1 is that orbital distance r1. All right, so let's think about this. So I've got point P, and I've got, here's going to be mass m1, and it's at radius r1. So that r1 is going from P to the middle of m1. And then you've got another object here. Okay, so this is m2, and it's a distance r2. Again, r2 is going from point P to the center of m2. Okay. Now, what I do know is that, well, when these two stars are orbiting each other, and actually, now that I think this picture is actually incorrect, since they have the same orbital period, they're always going to be across each other at the same point in space. So this is actually incorrect. It should always look like this. If they're always orbiting with the same period, that means they're going through the same angle at the same time, so they'll always be opposite each other. Okay, that is actually a very important conclusion, because when you look at the force of gravity acting on either one of them, force of gravity depends on not just the masses, but the distance between them. And the distance between them is non-varying because they have the same period. Okay, so the distance between them is r1 plus r2, always, and that doesn't change. Okay, so what I'm going to do is look at this from the perspective of one of these masses. Okay, so why don't we look at this from the perspective of mass m1. Okay, so I know that the gravitational force acting on mass 1 is equal to the centripetal force acting on mass 1. Now, gravitational force requires two masses. Okay, so the two masses here are m1 and m2. So that's going to be g m1, m2. Now, what's the distance between them? It's r1 plus r2. It's the distance that gets squared. Okay, so now you can already see where this part's coming out from. So divided by r1 plus r2 all squared. The centripetal force on 1 is going to be equal to mv squared over r. And this is fc1, so it's m1 and r1. Okay. In our formula, we have a 4 pi squared. You know, that usually comes out when we find that speed is equal to distance over time. The distance moving in a circle is 2 pi r. So in this case, the speed for, well, anyways, well, let's get the general expression first and then we'll make it specific. The time for one orbit is capital T. And so v squared we always see is 4 pi squared r squared over t squared. Okay, so this in the case of, well, speed 1 technically, okay, so that will be v1, so it's 4 pi squared r1 squared over t1 squared. So I'm just going to make that r a capital when I plug it in over here. So on the right I have m1 over r1 times v1 squared. v1 squared is this. 4 pi squared r1 squared over t1 squared. Okay, so I can see some cancellations about to occur, at least one. I see r1 can cancel with one of these r1s here. Okay, so that means I'm left with m1 over t1 squared times 4 pi squared r1. And that's equal to g m1 m2 over r1 plus r2 squared. Okay, so I notice that m1 is appearing on both sides. So I cancel that out. Let's see here. And in the original expression that I'm trying to get to, I'm isolating for t. So let's isolate for t. I think we might actually be there already. So if we rearrange for t, I'm going to take this t1 and I'm going to bring it to the top left. I'm going to take this numerator in the top left, bring it to the bottom right, and take the denominator on the bottom left and take it to the numerator in the top right. Okay, so t1 squared is equal to, so in the numerator here right now I have 4 pi squared r1, and I'm going to multiply that by, so this is getting multiplied over r1 plus r2 squared, and I'm dividing by gm2. Now you can put gm2 over the whole thing, you can just put it over one piece. Let's just put it over the whole thing because they're all being multiplied and divided. Okay, so this is essentially what we have up here, right? Except here we just have the constant together and then the r1 plus r2 squared together. But I mean, that's essentially it. We've derived the formula. Just to make it look nice, we're going to make it look like how they had it. So t squared is equal to 4 pi squared over gm2 times r1 plus r2 squared. Now the reason I could drop the subscript 1 and just make it a t is because the question tells me the stars have the same orbital period t. So that means t1 is the same as t2, so you can just call it t. Okay? So that is our derivation, and we have arrived at the correct final expression. Okay, let's go back to the slides. And of course, the answers are all typed up here if you want to look at that, but it's the same as what I've done on paper. All right, part C. The star of mass m1 is closer to the point P than the star of mass m2. Using the answer in B, state and explain which star has the larger mass. Okay, I'm going to need another piece of paper for this. Okay, so which star has the larger mass? All right, going back to the paper here. Okay, so this is essentially the expression we found. Now, we know that that was originally found as T1. So let's take a look at this. Okay, so T1 squared is equal to 4 pi squared R1 times R1 plus R2 squared all over GM2. But if you were to have solved this differently, so let's say you didn't use gravitational force on 1 or equal to centripetal force on 1, maybe you did Fg2 is equal to Fc2, you would have come up with an expression very similar to this, but instead of R1 here, you would have had R2, instead of M2 here, you would have had M1. And of course, this would have become T2, not T1. Everything else would be the same. Okay, and that's just because of the symmetry of the problem. You can always solve it just to confirm that that's the case, but that is in fact the case. Okay, so what that means is due to the symmetry, we can state that T2 squared is equal to 4 pi squared R2 instead of R1. Now we still have R1 plus R2 squared. That's still the distance between them, except now we divide by GM1, not GM2. So hopefully that's okay for you. And now we're told in the question that the periods are the same. So T1 and T2 are the same. And if T1 and T2 are the same, that means that T1 squared and T2 squared are also the same. So T1 squared equals to T2 squared. Okay, so we're going to go ahead and set these two sides equal to each other. So 4 pi squared R1 times R1 plus R2 squared over GM2 is equal to T2 squared. So 4 pi squared R2 times R1 plus R2 squared divided by GM1. Okay, time for some cancellations. G appears on both sides. 4 pi squared appears on both sides. R1 plus R2 squared appears on both sides. Okay, and that's as far as our cancellations go. Okay, so that means we're left with R1 over M2 is equal to R2 over M1. Okay, so I mean, we're almost at a point where we can do this comparison. All right, so let's be smart about this. We're trying to compare the masses, the radii. Hang on a second, let me check the question again. State and explain which star has the larger mass. Yeah, okay, we're comparing masses. So let's get the masses on one side and the radii on the other. So let's do this. So M1 over M2, so multiplying this to the top, taking that, bringing it to the bottom, is equal to R2 over R1. Okay, now what I know based on the picture and based on what I've already drawn too, is that radius 2, this is bigger than radius 1. So the numerator is bigger, okay, than the denominator. Right? So if the numerator is bigger on the right, I mean, that means that the numerator's got to be bigger on the left as well. Okay? So that means the M1 has to be bigger than M2. So M1 is greater than M2, and this is how we compare the masses. Hopefully that's okay. Okay, and again, the same answer is typed up here, so you can go through it. Okay, so that is it for 6.2, a Newton's Law of Gravitation. Stay tuned for further instructions and, of course, more videos for future units. But that does mark the end of this unit on circular motion and gravitation.